In this video, we're going to review a couple of rules of probability, things that you've been reading about in the textbook and elsewhere, and then I'm going to show you how they can be applied to even the simplest risk assessment. In fact, they must be applied to even the simplest risk assessments, and that's why you're going to need to be fluent in these rules. You don't have to be a technical expert, but you have to recognize that there are rules and that you must follow them. Here I have a table in front of you that's showing you some data. In the columns, we have whether a person is positive for disease, D plus, or negative for disease, D minus. Then there's a total of both columns. In the rows, we have whether a person tests positive, T plus, or they test negative, T minus. We begin by talking about a marginal probability. A marginal probability is the probability of a single event. Notice the syntax. Probability of A. The thing inside the parenthesis is the event whose probability we're after. So you can just think of A as standing for anything. When you are doing risk assessments, you're going to be interested in probabilities because probability is half of that equation that we've talked about a number of times. So probability is indeed important. Here I give you a couple of quick examples. The probability that a person has the disease, D plus. Ordinarily, we don't have data like you see in the table, but with the table, this becomes easy. I look at the total for column D plus, it's 100 out of 10,000 people. That's a 0.01 chance, or a 1% chance. The probability that a person tests negative, 9,806 people out of 10,000 tested negative. So that probability is 0.9806. The next thing to know is the complementarity law. This is basically saying that if you have all the possible outcomes, the probability of all those outcomes when summed together must equal 1. In this example, looking at disease, we only have two possibilities. Disease positive or disease negative. So both of these together must sum to 1. If I tell you that the probability of being disease negative is 0.99, then its complement, given by the third bullet there, notice that strike mark next to the D negative, that means everything but. So we might read that the probability of being everything but disease negative is equal to 1, the probability of everything, minus 0.99, which is the probability of being disease negative. So once again, the probability of being not disease negative is 1 minus the probability of being disease negative. The complementarity rule you'll see used several times in the example I will show you at the end here. There's a general rule of addition. In risk assessment, we're often interested in more than one event. It can be much more than 2, but to keep the arithmetic simple for now, let's begin with 2 events, A and B. In the second bullet there, you see the general formula. The third bullet translates this general formula for our table, so let's begin at the third bullet. What's the probability that a person is disease positive or that they test positive? Well, to get this, you take the probability that a person is disease positive. That would be 100 out of 10,000 people, and you'll see that number in the last bullet. To it, you add the probability that a person tests positive, and that's 194 out of 10,000 people. Now, from that, we have to subtract the probability that a person is both disease positive and that they tested positive. In our table here, to get that particular number, you would go to the intersection of the D plus column and the T plus row. Notice the number 95 there. So 95 out of 10,000 people were both If you look at the last row, the arithmetic says to get this number, you take the 100 people who are disease positive. So look in the table. The disease positive column comprises 95 people who tested positive and 5 people who tested negative. To that, we add the number of people who test positive. Looking across the row, we see that's 95 people who have the disease, and we just counted them a moment ago. So if I count them again now, I'm counting them twice. But let's continue. So we have 95 people who have the disease, and we have 99 people who don't have the disease. That gives us the total of 194. But now we know that when we add these two numbers, we've added that 95 in twice. So we have to subtract it out once. And that's basically what happens with the second part of this formula. There are also multiplication rules for probability. They're a little less obvious. It really depends on the relationship between events A and B. If these events are independent, then the probability of A and B both occurring, and that's called a joint probability. So the probability of A and B both occurring is the probability of A times the probability of B. If the events are dependent, however, and in our table they are dependent, whether you have the disease or not will affect the test. And how the test turns out gives us information about whether you are likely to have the disease or not. So for our table, we would be working with dependent events. And there, that joint probability depends on the nature of this dependency. And that's often a nature that is unknown to us, one that we are guessing at. It turns out that, at least for arithmetic purposes, there is a general rule of multiplication. And it says the probability of A and B, or that joint probability, is the probability of A times the probability of B, given that A has occurred. Now, that given bit that I just mentioned, that's a conditional probability, and we haven't considered that yet. So hold on for a few moments. I'd like to conclude this slide by pointing out that when you're doing risk assessment, you're working in the real world, and reality involves a lot of dependent relationships. So it's likely that if you need the multiplication rules, that you'll be working at that second big bullet for dependent events. Here's a simple example of the multiplication rule, where we're looking at the probability that someone is disease positive and they test positive. So I have translated the rule and basically said that's probability that you're disease positive, looking at the table, that's 100 out of 10,000, or 0.01, times that conditional probability that you test positive given that you had the disease. So we're going to talk about conditional probabilities in the next slide, but let's look here for the first time. I have some information. Your table gives us information about 10,000 people, but that last probability term in the second bullet says we're looking at disease positive people. So we're no longer looking at all 10,000 people. I'm just looking at the data in that column for disease positive. I'm just looking at those 100 people there. And this asks, what's the probability that you test positive given that you are disease positive? So that's 95 out of 100 people, the 0.95 that you see in the last bullet. When you complete that multiplication, you have the probability of being both disease positive and testing positive. That joint probability is 0.095. Now notice this. If we were fortunate enough to have a table like this, complete with all this information, we didn't have to go through that mathematics. I could have just looked at the table and read it off. The probability of being disease positive and test positive means how many people are in that part of the disease positive row that intersects the test positive row. And I see a cell there that has 95 out of 10,000 people. So had I had this table, I could have just looked at this value. When you're doing risk assessment, you're not going to have all the information you'd like to have. In fact, you might even have to estimate some of these numbers. But when we have just the numbers, we can calculate this probability using that second bullet here. Now let's look briefly at conditional probabilities. It turns out that information can change probabilities, and that's going to be a really powerful tool, a very useful idea for us to keep in mind doing risk assessment. But looking at the second bullet, we see, and let's look at the syntax now, the probability of A, and that vertical line is read as given that. So the probability of A, given that B has happened, is not the same as the probability of A if A and B are dependent upon one another. That you may need to think about a little bit. This isn't terribly intuitive. It does take some effort. At bullet 3, we have defined how you would calculate the probability of A given B, and that's a simple fraction here. It's the joint probability of A and B divided by the probability of B. So in the fourth bullet, I translate from A and B to values from our table. What's the probability that a person tests positive given that they're disease positive? And we're not going to do the arithmetic right now. I just want you to look at the table. I'm getting some information. We're being told that this person is disease positive. So we're no longer interested in all 10,000 people. We're only interested in those people in column D+, and there's 100 of them. And this question says how many of them test positive for the disease? It's 95 out of 100. So just as we saw in the previous slide, we have a probability now of 0.95. Notice that the probability of testing positive, given that the person is disease positive, is different. It's 0.95. The probability that you test positive is 0.0194. So looking at these two last bullets, both of them are probabilities of testing positive, but they're very different numbers. And that's because we have some specific information for bullet 4, and in bullet 5 we do not. That's a lot to absorb. So what I would like to do now is to move on over to use one of our tools for the course. This is Precision Tree. You'll notice that I have transferred the table over here, and I've basically taken the information in the table and put it in tree form. So I've called this model a test for disease, and the very first node asks disease, yes or no. The top branch is disease positive, the bottom branch is disease negative. And you'll see there the numbers transferred over from the table, 1% and 99%. Okay? Moving over into column C now, we have the next event, and that is how the test turns out. So moving off the top branch, disease positive, we look here and we see test positive. Among the people who are disease positive, 95% tested positive and 5% tested negative. Look down here at this branch. Of the people who don't have the disease, 1% tested positive, 99% tested negative. Now what this model does is it completes the arithmetic for us. So this value here, 0.95, that is the number of people who both had the disease, 1% of all the people had the disease, and 95% of them tested positive. So you can see that just under 1% of the people both have the disease and tested positive for it. If we move down to this next cell, we see that 0.05% of the people have the disease but tested negative. And that would be a number that we would like to get as close to 0 as possible. Continuing down, you can see that among the people who don't have the disease, 1% of them tested positive. And that's almost 1% of the total population. We go to the final entry, and we see here that 98.01% of all the people do not have the disease, and the test confirmed that they do not have the disease. So now we're going to turn our attention to column F. Column F has many of the concepts that we were just looking at. And what I would like you to realize is that in building a model as simple as the one that we just reviewed here, you need to know those rules of probability. So let's take a look at probability that you test positive. Where would you get this number? Excuse me for that. Where would you get this number? Well, it turns out I have two endpoints. Here's a test positive, and here's a test positive. So when I click in this cell, have a look up here at my formula bar, which basically says to get the probability of testing positive, I'm going to add those two numbers. And so when I do, I get the probability of 1.94%. And if you were to go back through our earlier presentation, you would have seen that was a number that we calculated. This 98.06%, this happens to be this number plus this number. So we are gathering up endpoints here that are of interest to us and summing them. The probability that you're disease positive, this is just read directly from the model. And the probability of disease negative is also read directly from the model. So let's use this moment to point out the complementarity rule. If I happen to know what number of people have the disease, then I would automatically know the number of people who don't have the disease. That has to be everyone else. So notice that when you build a model, these branches, I only have two in a simple model, these branches have to sum to 1. Likewise over here when we talk about the test probability, it has to sum to 1, and it does. This must sum to 1, and it does. You won't always have two branches. Sometimes you'll have more than that. But in this simple model, let's point out that we have 4 endpoints. The triangles here are endpoints. And so this plus this plus this plus this must sum to 1 as well. And if you'll check the arithmetic, you'll find out that they do. Now let's look at what's the probability that a person is disease negative. As I mentioned, we just copy that from the model here. So now that we've gotten all 4 of the marginal probabilities, we can move on to a more complex probability. Here we have a probability of 2 events. What's the probability that a person is disease positive or they test positive? Here's how we would get this. The probability that a person is disease positive is right here. We are going to add to this the probability that they are test positive, 1.95. Then we add the probability that they are test positive down here at this node. And you will notice perhaps that we have counted this value twice, so it must be subtracted out. So if you look in the formula over here, I've calculated this longhand for you to show how we apply the rules. We add up the two individual probabilities, and then we subtract that which was double counted. And this brings us to the same value that we saw earlier in our slides. 1.99% are either disease positive or they test positive. The next probability that we're after is a joint probability. The probability that a person is disease positive and they test positive. Next to that, you will see the formula. And it's actually quite simple. If you take a look once again in our function bar up here, you will see how we calculated this. It's this number right here, disease positive, times that conditional probability right here in C1. So this number times this number gives me that probability. Okay? And that's a simple application of this rule. The probability of being disease positive is right here. Notice in our model in column C, here I have test positive, but it's preceded by this. So this is telling me this event has already happened. I already know this person has the disease. Given that I have that information now, I know there's a 95% chance this person will test positive. So this is the value here, the probability that they test positive given disease positive. So once again, we multiply those two together to get this value. The last thing we're going to do with this model is we're going to take a look at how you would get a conditional probability. Specifically, the probability that you test positive given that you are disease positive. Now this is easy. We can just read it off right here. That is the value, 95%. But let's look at how we would do this if we just had numbers. After the equal sign, you see a joint probability. Test positive plus disease positive. And that's the value right here in cell D1. So I would take this value, divide it by the probability of being disease positive, 1%, and that would yield the overall value here. So look again up here in the formula and you will see that value. This model is available for you in the course materials. And when you're hearing this for the first time, or for the first time in a long time, it can really hurt your head. But what I would like to do is have you focus again on column F and see that all of these rules, these are all used to build a model as simple as this. Event tree models are very handy risk assessment tools. And so to build this model, we've had to use most of the probability rules that we just reviewed. So once again, I would like to stress that you need to be fluent in these rules. You don't have to be the technical expert, but you have to know that there are rules that apply here. Okay, that's going to be very important. Let me point out one last thing. If you look at the probability of testing positive, for those 10,000 people, we would say 1.94% of them are going to test positive. But look in the model here in column C. We have two values for testing positive, 95% and 1%. Neither one of them is 1.94%. So if you didn't know these rules and you put 1.94% in here and 1.94% in here, you would get wrong answers and nonsensical results, and that clearly would not lead to good decision making. But because we know that testing and having the disease are dependent events, we know that conditional probabilities are going to look different than the overall probability. So these are some of the reasons why it's important for you to understand these rules of probability. So if you've got questions, please feel free to ask them in class. Also, please feel free to go back and review the material as much as you need to, and then come with your questions.